So good evening, everyone. Let us carry forward with the course contents of for the third week. So in this in the third week course, we will be basically studying about the data collection procedure for environmental related aspects, and also try to understand the LCA methodology, how to start and like how to proceed how to proceed forward for performing the life cycle analysis. So let us start. So 11th lecture is basically on this only, environmental data collection and LCA methodology. So for basically analyzing chemical, for performing any type of chemical related analysis, there are various types of procedures. So one is direct chemical measurement. So there we directly use perform basically titration of samples for alkalinity or hardness, or we can use a sensor or an instrument such as a pH meter or chromatograph, or in many cases some form of sample preparation will be necessary. So the sample preparation and analysis, if we see, so basically between sample and analysis there are two steps. So one is the physical preparation, and one is the chemical preparation. So if we talk about physical preparation, so it can be of various types such as mixing, drying, grinding, etc. For chemical preparation, we can go for acid digestion, solvent extraction, and chemical oxidation. And for analysis, basically we use titration, electrode, and other instruments. This is mainly for environmental related analysis and data collection, basically related to environmental science. So, in case of instrumental analysis, we will find that many different instruments have been developed to measure the concentration of pollutants in environmental samples, and these instruments give a response that correlates the amount of sample present. So, basically, they will give some value. So, this value, which is the response, so that can be in terms of conductivity, that is increase or decrease in conductivity. Second is the absorbance of light, and third is the emission of light. So they will give some value, and that value can be correlated with some that can be correlated with some standard values, which can basically give the amount of sample present based on the response of the conductivity and emission absorption that is received. Okay, so that using some standard chart we can predict the amount of sample that is present of certain pollutant or of any some certain substance basically. So this is this is the process. So if we plot the response and concentration, so to say for example this is a standard chart. Okay, this line signifies a standard chart, and these are some of the values which you have obtained from the analysis, which is represented by the four dots. So by correlating the response value, we can find the concentration value. So for this rate, this was the response we got from the experimentation. So from that we can find that in the sample the particular substance has a concentration of this. Okay. Similarly is the case with this and this. So for performing this instrumental analysis, so we basically use spectrophotometers. So they basically measure the absorption of light at specific wavelengths, and some chemicals are directly proportional to absorbance. So that also helps in finding its value. And many methods that were developed based on color changes in titrations can be also measured using absorbance. So that is also an added benefit. So, in order to perform some type of quality control and quality assurance, so that we are assured that we are guaranteed that the values obtained are correct. So there are some various types of QC and QA checks. Okay, so they are designed to make sure that the data that we gather are sufficiently accurate, precise, as well as repeatable. Okay. So this is the main reason for which we should perform some QC and QA checks. So some of the mechanisms for performing those are: one is blanks, that is the use of blank sample. So blank sample is basically a sample which does not have any concentration of our uh, targeted sample. So it should not have. So by checking that, we should get a value which is showing nil concentration basically. So that is a blank. Spikes is basically when in the sample we are adding some known substance at a known concentration, and we are correlating with the chart and seeing that it is also giving the same concentration as we had predicted, because we knew the amount of concentration which we had added. So that is basically called spiking. So that is the concept. And third is the replicates. So basically we are simulating some substance, okay, using some other substance and trying to find that whether it is providing the similar value. So basically it is a replica. So replica is like we are basically it is a repeat, some type of repetition. So we are not actually getting we are not actually we are basically not taking the actual sample. We are taking some other samples and trying to simulate and find out whether it is the values which we have obtained are close to the targeted sample value. So that is also replication. Okay. So basically, the plan for the QA project, the plans are list of detailed activities performed at each stage of the dredged material or the considered material evaluation, and outline project-specific data quality objectives that should be archived or recorded for field observations and measurements, physical analysis, laboratory chemical analysis, and biological tests. So, sorry. So for in order to achieve that, so there are various steps such as various strategies. One is the standard operating procedures involved. One is the sampling strategy and procedures involved. One is sample custody. One is calibration procedure and frequency. One is analytical procedures. One is data validation, reduction, and reporting. One is internal QC checks. One is performance and system audits. One is preventive maintenance. One is calculation of data quality indicators, and one is corrective actions. So these are some of the processes which need to be adopted for assuring quality control. So this is some of the plans. So these are some of the factors that have to be taken into account. So in this regard, one important parameter is the method of detection limit, or the method detection limit, which is also abbreviated as MDL. So that is basically the minimum concentration of a substance that can be measured and reported with a 99% confidence that the analyte concentration is greater than zero, and is determined from analysis of a sample in a given matrix type containing the analyte. So that is the definition provided by EPA, or Environmental Protection Agency, in 1992. So basically, the analyte is a substance whose chemical constituents are being identified and measured. So that is the targeted substance. So the minimum, sorry. So the detection limit is the minimum concentration of that analyte substance which can be measured with a 99% confidence. So that is the minimum value which can be measured with 99% confidence, so that it is greater than zero. So that value is the detection limit. Okay. So that is the minimum concentration, and the process is called MDL, or method detection limit. So MDL basically we can find out using this formula. So one is the basically MDL relates the one-sided critical T value and standard deviation. So it is equal to T into S, where T basically is a value which is equal to n minus 1, and alpha is equal to 0.99. So because it is a one-sided critical T value, so it is having a confidence level of 99%. So in here, this case, alpha is basically the confidence level. So generally alpha signifies the significance level. So confidence level is generally 1 minus alpha. So but in this case, alpha is basically the confidence level and not the significance level. Okay. And n minus 1, basically we always take one sample lesser the total sample. So that is why it is n minus 1. So T is the one-sided critical T value for n minus 1 samples at a confidence level of 99%, and multiplying this with that standard deviation, we basically get the method detection limit, or MDL. So let us see an example. So for example, if this is a sample, these are some of the results of an analysis of some samples, and of a particular sample, and the analysis results have been given for 8 number of samples. So we see that sample 1 has 12.11, then 12.02, 12.21, 12.06, 12.57, 0.42, 0.09, and 12.32. So these are some of the results obtained experimentally for a sample. In this case, the method detection limit can be calculated as such that n is equal to 8 because we have 8 samples. Standard deviation, if you calculate, we will get the value as 0.19. So basically, the one-sided critical student t value, student t characteristic value, t will be for 7, that is 8 minus 1, and alpha for 99% confidence, that is 0.99. So t value will be 3.00. So basically multiplying 3.0 with the standard deviation, that is 0.19, we get the method detection limit, which is basically equal to 0.57 milligram per liter. So this means at given results, 0.57 milligram per liter is the method detection limit. So it indicates that 0.57 milligram per liter would be minimum concentration you can trust with 99% confidence level when you have achieved these values as the analysis results. Okay. So this is the minimum value you can trust with 99% confidence level. So that is the method detection limit. So this is the detection limit basically. So let us go to the 12th chapter lecture, sorry, which is the environmental data collection in LCA method. So it is continuation. So here some of the it lists some of the techniques. Okay, so it lists some of the techniques through which we can find out the values of various values such as conductivity, absorption, etc., spectroscopic values. So that can be correlated with some standard chart and or standard graphs, and from them we can find the analyte concentration of our target sample. So the various techniques, some of the important techniques which are used in this process, let us study one by one briefly. So one is the ion exchange chromatograph. Okay, so chromatograph is basically the study of diffusion of a sample in some mobile phase. Okay, so the how it diffuses, what is its flow parameters. So based on that, we can identify a sample. So that the study of basically, it is a characterization technique which uses the flow properties of a sample to identify its constituents. So, okay, so that is the chromatograph. That is a technique. That technique is called chromatography. So there, one of the technique is ion exchange chromatograph. So ion exchange chromatography is basically used to analyze liquid samples for dissolved ionic or polar materials by charge properties. So as the name suggests, so this uses this basically is used in liquid samples to detect the ionic or polar materials present by virtue of its charge properties. So it uses the charge properties to find out the ionic or polar materials basically available in liquid samples. So that is ion exchange chromatograph. Second is the gas chromatograph. So gas chromatograph is an instrument to separate complex gas or liquid samples to single components. So it basically there basically the injected samples are separated in gas phase, that is a mobile phase, through the column, and separated components are detected by various types of detectors such as flame ionized detector, that is FID, and thermal conductivity detector, which is TCD. So these are some of the techniques which can find out the constituents or the separated components, what are those, and basically gas chromatograph, by virtue of its flow properties, it is able to separate the various gas phases which are mobile in the column, and using the detection techniques such as FID and TCD, we can characterize basically the separated components. So similarly, one more gas chromatography technique is GCMS, that is gas chromatograph mass spectrometry. So in this case, what happens is we basically use mass spectrometry for detection. So that is basically we basically find the mass per charge ratio. So that mass per charge ratio uh, by calibrating, by equating with the known values, so comparing with the values, we will be able to detect what is the constituent material. So GCMS is a GC equipped gas chromatography equipped with mass spectrometry as a detector. After complex chemicals are separated through a GC column, as happened here also, only here also. So after it is separated through a GC column, separated components are fragmented by high energy source in a mass spectrometry in order to find the M by Z or mass by charge ratio. So with size and patterns of those fragments, components can be identified. So this is the technique basically used. One more technique is the high performance liquid chromatograph or HPLC. So like other chromatograph, an HPLC is also used to separate complex chemicals to single components. Unlike a GC, HPLC uses liquid as a mobile phase. GC basically, as the name suggests, it uses gas. Okay, so it uses gas as a mobile phase. But in case of high performance liquid chromatograph, it uses liquid as a mobile phase. The separated components can be detected by UV VIS or ultraviolet visible absorbance detector. Since an HPLC can handle only liquid sample, more complex and greater molecular weight chemicals can be analyzed. So this is the usefulness of using HPLC, because it only handles liquid sample. So therefore very complex and greater molecular weight chemicals can also be analyzed. Next, let us go to LCMS, that is liquid chromatograph mass spectrometry. So this is the equivalent of GCMS in liquid form, in liquid phase. So like GCMS, LCMS is a LC equipped with mass spectrometry as a detector, and LCMS can be used to analyze large molecules such as pharmaceutical products and protein. So as the name suggested, it suggests, so the liquid chromatograph is equipped with mass spectrometry as a detector, and as it uses liquid phase, so it can be used to analyze very large molecules or very heavy molecules, such as those molecules which are related to pharmaceutical products and proteins basically. So these are very much useful in biology and health related, medicine related field basically. One more way is to use the inductively coupled plasma or ICP. So this coupled plasma ICP, when it is added with AES, that is atomic emission spectroscopy, so it, it is used to analyze elements such as heavy metals and cations using an inductively coupled plasma ICP. So here each element can be recognized by electromagnetic radiation produced by excited atoms at a particular wavelength of a particular element. So each particular element will have some particular wavelength at which the atoms get excited. So by comparing those wavelengths at which the atoms have been excited, so we will be able to detect that particular element. So this uses the concept of electromagnetic radiation at a particular wavelength to find out the excited atoms at that wavelength, and therefore be able to predict the element present in the substance or the sample. So like this, each element can be recognized. So that is the way how ICP, inductively coupled plasma, is uh, carried out. This test method is carried out, and it uses electromagnetic radiation. So one more is the atomic absorption spectrometer. So, uh, basically it is used in conjunction with this only ICP only. So this is the photo of that atomic absorption spectrometer. So it is similar to atomic emission spectroscopy, same thing only. So so these are some of the techniques basically. So now let us see what is the importance of statistical calculations, okay, when working with this type of concentrations. So statistical calculations are often needed when working with concentrations. This is because since concentration results are often directly used as a part of regulatory decision making, that is it a hazardous waste, is it safe to be land applied, it is necessary to perform a statistical analysis. So basically statistical analysis is important because it helps in the regulatory decision making, okay, because we are basically, when it comes to the domain of environmental science, we are basically studying waste and those substances which are not good for the environment, okay. So is it a hazardous waste, is the waste safe for land disposal, etc. So it is very important to have a foolproof and very comprehensive knowledge of the data which we are or the concentration which we are working with, okay. So to get a very good support to get good support with statistics is a very beneficial thing and important thing in regulatory decision making. So therefore comes the uh, prospect of statistical analysis. So what is the chemical concentration of a waste? Very rarely are waste or contaminated soils completely homogeneous or with respect to chemical concentration. So that is obvious. Each like not it is not consistent, so it will not be homogeneous somewhere it will be more, somewhere it will be less, depending on the location and the proximity of that waste from that location. Okay, so it will be not homogeneous. Ideally we can consider, but actually it is always heterogeneous, and therefore we must collect and analyze multiple samples to determine what some representative concentration is. So it is very important therefore to collect and analyze various samples taken from various locations in order to determine what can be a representative concentration of that area. The more heterogeneous the matrix, the more samples may be needed to accurately describe the representative concentration. So that is obvious. That is the concept of sampling. So more is the heterogeneity, higher the number of samples required to accurately signify or represent the concentration or the population basically. So in order to accurately describe the representative concentration, more samples will be needed for a more heterogeneous matrix. Okay. So what is this representative concentration? So how, what can be that ideal representative concentration can be, should be or can be? So let us think. Okay. So according to statistics, some estimate, it can be some estimate of the central tendency. Okay, so as per the statistics, it can be some estimate of the central tendency. So that central tendency is nothing but it can be the mean, which is average. It can be the median, which is the middle number, or it can also be the mode, which is the most common number. So these are some of the very standard trivial terms which we use in statistics, and that is that can be estimated. So the central tendency can be estimated from this, or it can be some upper or lower confidence limit. So it can be some value which with which we can be assured, say we can have a confidence level of 95%. So we can say that this is the maximum limit, like with a confidence level of 95%, this is the maximum limit. That means out of 100 samples, 95 samples will always have value lower or equal to that, and 5 may be there which can be higher. Okay, and similar is the case with lower confidence limit. So that can be also a type of central tendency. And apart from that, one of the important parameters to consider is the sample distribution. So the sample distribution has to be very much reliable. So we cannot just assume a sample distribution and perform only analysis and later find out that that distribution did not actually match the values of the samples. Okay, the values of the data set basically. So we have to ensure that the data set values are the sample distribution which we're designating for a particular data set. So it should be reliable, it should match properly. And we should also consider what that data will be used for. Is it used for, will it be used for analysis, will it be used for research, or will it be used for some regulatory decision? So that is also, so what is the motive of that data? Okay, so what is the target of that data? So that is also an important consideration in this respect. So basically, in environmental science, when we are working with this type of aspects, so basically there are two types of sample distributions which generally come. Okay, and mostly this the second one, that is the log normal distribution. So we will mainly encounter with this type of distributions. So either of these two and more of this. Okay. So one is this normal distribution, which is very much trivial. So it is such that it will have everything in the middle. Okay, so the mean will be middle, the mode will be middle, and also the median will also be in the middle. And second is the log normal distribution. So this is a type of distribution where there is skewness. Okay, so it can be either this way or it can be like this also. Log normal here, so because log is left, so it is left the logarithmic, and right is normal. It can also be normal log also. Okay, so this is a type of distribution which we will basically encounter when we are working with, and when we are working with sample data related to concentrations and environmental science related aspects. Okay? So let us take an example. So uh, so in order to understand the type of distribution that dictates how to calculate the central tendency, so let us take some examples. So say for example we have got some toxicity characteristic leaching procedure or TCLP results. Okay, so let us consider the following data set for some TCLP results which are given in milligram per liter. These are the values 3, 2, 3, 5, 4, 4, 5, 7, 8, 1, 6, 2, 5, 9, 6, 5, 7, 7, 3, 4, 2, 8, 5, 4, 5, 6, 6, 3, 5. So these are some of the data which we have obtained for from TCLP calculations. Okay. So here if you check the value of the total number of samples, capital N, that is equal to 29. Okay, so if we plot this data as a histogram, and if we see the distribution, we will find that the resulting distribution has a similar shape as a normal distribution. It is almost similar. Okay, it is like this and it is like this. Okay, and the mean appears to be a good estimate of the central tendency. So that can be seen from here also, that it is a normal distribution. So the mean, median and mode almost all are almost equal. Okay, so mean is around 4.83, which uh, if you if you round it off to 0 decimal places, it will become 5 only. Okay, so arithmetic mean 4.83, rounding off to 0 decimal places, it is 5 milligram per liter. Median is 5 milligram per liter, and mode is also 5 milligram per liter. So it is a very good distribution or normal distribution. Okay, however, if you consider this the data set, okay, so this is a different data set. So it has 31 samples. The values are 3525334371724955116262284246164233. So these are some of the, this is a different data set having a sample number of samples as 31. So if you see here, so this is basically not a normal distribution, it will be mostly a log normal distribution. So it is skewed in the right. Okay, so the resulting histogram gives the appearance that it might be a log normal distribution. So that is true, and that means the mean appears to be somewhat less reliable as an estimate of central tendency. So in this case, as you saw, everything was equal. Okay, and if you would have calculated the standard deviation and variance, that would have been very less. Okay, very less than the mean and median and mode. So we could have said that the mean was a reliable central tendency value. Okay, so we can say that mean could be the representative value. But in this case, if you see, everything is different. The mean is 5.32 milligram per liter. Okay, the median basically is 4 milligram per liter. So both of them are having a uh, difference of more than 20%, right? So if it is more than 20%, it is not, we cannot say both are equal. Okay, and similarly, if you compare mean with mode, which is 3, so it is having a difference of more than percentage, the difference of more than 40%, right? So that is, therefore we can say that mean appears to be somewhat less reliable as an estimate of the central tendency. So it can be used in this distribution as a representation. Okay, so therefore, if we go into more detail, so if you see the first data set, so as we just saw, so it had 29 data, 29 the frequency of the data set was 29, that is 29 values. So here, if you can calculate, okay, if you calculate, you will find the standard deviation for this data set is 2. Okay, and the variance is 4. As we all know, standard deviation is square root of variance. Okay, so square root of 4 is 2. So it is likely that the data is normally distributed. Why? Because the deviation and variance is very much lesser than the mean. Okay, so since standard deviation variance is lesser than the arithmetic mean, so we can definitely say that 4.83 can be a representation of the data set. Okay, however, in this case, the second case where we had 31 samples, here if you see, the standard deviation is 4.1, but the variance is 16.8, much higher than the arithmetic mean, which is 5.32 milligram per liter. Okay, so if you see the difference, it is more than 200%, right? It will be more than 200%. So if you see, because the standard deviation and because mainly the variance is very high to the mean, so that means the data is not, it is likely that the data are not normally distributed. So we cannot simply say, because it look something like a so if you see from the figure also, we can see that it is not normally distribution, and by calculation, by proper proof, we are able to say that it is not normally distributed. Why? Because the variance is much higher than the arithmetic mean. So that means we cannot take the mean as the representative value. Okay, so it is likely that the data is not normally distributed since the variance is higher than the arithmetic mean. That means mean can be a representation of the second data set. So the question next arises is, how do you handle data that are not normal? How to handle those data which is not normal, which is not normally distributed? Okay, so the answer is, or the steps to follow there is, firstly we have to check, first step is to check to see whether the data are log normally distributed. So if it is not normally distributed, the second option will be to check what is if it is log normally distributed. Okay, and most of the, as I told you some slides back, most of the environmental data are often log normally distributed. Okay, so if it is not normal, it mostly it should be log normal distributed. And there are also, in order to find a log normally distribution, what we do is we perform a log transform on the data and check for normality again. Okay, so in order to find whether it is log normally distributed, what we do is we take the data set and take its logarithmic value. Okay, so we apply the ln or log e value. We find or calculate the log e value for all the samples and all the data, and find the new data set. Okay, the transform data set, which is log e of the x value, which was the actual data set. Okay, so if we talk about the second data set, say for example, so the initial data was this one, initial actual data set was this one, which are 31 value. So this was the actual data. So now we will take log e value. Okay, so we will take log e value of all these values. Okay, so if you take the log e values of all those values, and if you find the arithmetic mean, so that will come to be 1.46. So you can calculate it. So it will come to be the arithmetic mean will come to be 1.46. And in that in that case, if you check there, you will find that the standard deviation is coming to be 0.65 and the variance is coming to be 0.42. So both of them will be very much lesser than the arithmetic mean, which is 1.46. Okay, so that means that the mean of the transform data is greater than the standard deviation and variance of the transform data, and that means that it is thus reasonable to treat the original data as log normally distributed. So if the variance and standard deviation is very much less than the arithmetic mean, so we can say that it is the consideration of the log normal distribution is reliable, as can be even checked from the histogram itself. So it was a log normal distribution. So therefore, it is thus reasonable to treat the original data as log normally distributed. Okay, so we will consider the original data as log normally distributed. Okay, by transformation. So by transformation, we have considered the log normal the distribution of the actual data set, and when the mean of the transform data is again transform back. Okay, so then we get the geometric mean. So this is basically the mean of the transform data set. Okay, it is 1.46. Okay, but this is the transform data set, not the actual one, because we applied log e. Okay, now if we all know, right? So if we take log e of x, okay, and taking, say this is 1.446. Okay, so this is the arithmetic mean. Okay, so the log e x value of arithmetic mean is 1.46. So what is the arithmetic mean of x? That is x bar. Okay, so that is nothing but x bar is equal to e to the power 1.46. Okay, so this is some basic calculation of logarithmic. So I think you all know. So if it is like if the base of log is say 10. Okay, so then if we ask what is the value of x, so it will be x equal to 10 to the power the right hand value. Okay, so like that, if it is 20, it will x is equal to 20 to the power right hand value. Okay, so if e is 30, the x will be 30 to the power the right hand value. So similarly, if we, this is the mean arithmetic mean of log e x, so arithmetic mean of x, which was the actual data set, so that will be nothing but e to the power 1.46. So that is what it has been done. So if you do e to the power 1.46, you will get a value of 4.28 milligram per liter. So that is the mean of the transform data when transformed back. Okay, and that value, okay, that value is equal to the geometric mean value. Okay, so this 4.28 value, which was the mean of the transform data when transformed back. Okay, so when we did e to the power 1.46, we got 4.28 milligram per liter. And if you check the geometric mean of the actual data, okay, So geometric mean is basically using this, basically it is the nth square root of the product of the n values. Okay, so if you from mathematics, if you study, you will find that the geometric mean is n square root of product of n values. So if you find the geometric mean of these actual values, so that will also come to be equal to 4.28. You can check that. So that means the mean of the transformed data when transformed back, it is equal to the geometric mean of the actual data. Okay, so that is a relation. And this last question would be, what if the data is neither normally or log normally distributed? So if it is normally distributed, very nice, very good. If it is if it is not, then we will perform log. We will apply logarithmic. We'll apply log to all the data values, all the data set values, say ln or log e. So then, if the standard deviation or variance is lesser than mean, so then that means the data set is basically, the distribution basically is log normal distribution. However, if still the variance or standard deviation is greater than the mean, that means neither it is normal or it is log normal distribution. Okay, so for that case, what we will have to do is, we have to find another distribution, or we will use a more advanced statistical method, example a non-parametric method. So non-parametric method is basically, it refers to a type of statistical method that does not require the data to be analyzed to meet certain assumptions or parameters. Okay, so it does not need to be analyzed for like we don't have to find mean, median, we don't have to find out the standard deviation and variance to meet certain assumptions and or the parameters required to consider that whether that is the reliable distribution. So we don't have to perform any of such sort. So that is the non-parametric method. However, finding another distribution or going to advanced statistical method, so this is beyond the scope of this course. So for this course, we will be sticking to normal or and log normal distribution, because that is mostly associated with the environmental data. Okay, so this is beyond the scope of this course, but you are welcome to study it further. Okay, so now let us see how to incorporate uncertainty. Okay, so let us assume that the TCLP results which we just obtained, or which was presented for two data sets, let us assume that that was for lead. Okay, so that was for lead, which is a very hazardous substance beyond a certain limit. Okay, so let us assume that the toxicity characteristic or TC limit. Okay, so that, let us assume that that is 5 milligram per liter. Okay, so if you see here, if we see in this case, we will find that for dataset 1 we got an arithmetic mean of 4.83 milligram per liter, and for dataset 2, okay, the mean of the mean of the transform values, which was transformed, the mean of the arithmetic mean of the transform values which were transformed back, basically was equal to the geometric mean. Okay, and that was equal to 4.28 milligram per liter for the data set 2. If you see, if we just see here. Okay, so both value are, one is 4.83 and one is 4.28 milligram per liter. So both values are less than 5 milligram per liter. Okay, so these are based on a limited number of samples. Okay, and thus may be somewhat different than the true mean. So whatever we got these values, we are in a safe condition, because we have got a value which is less than 5 milligram per liter. But the question is, the number of samples which we have taken are very less. Okay, so this is based on the limited number of samples, but actually the case may be quite different. So there may be somewhat different condition or different situation where the values will increase. Okay, and therefore it will be very much different than the actual mean. Okay, so these values will not be equal to actual mean, because this is for a limited number of data set. Okay, so therefore we need to factor in this uncertainty factor. Okay, so we need to factor in this uncertainty, and for that purpose we have to calculate the upper confidence limit. Okay, so which is basically the UCL. It is abbreviated as UCL, and the UCL is a basically a conservative estimate of the mean that takes into account uncertainties in the data set. Okay, so it is a conservative estimate, that is it is basically a very pessimistic value. Okay, so we are taking more than what should be actually, what actually can be, we are taking even higher than that. So it is a conservative value, and estimate of the mean that takes into account uncertainties in the data set. Okay, and it is associated with some degree of statistical significance. Example, 95% UCL. So this statistical significance is nothing but the alpha value. Okay, so that means how much may be wrong. Okay, so for example, if we are talking about 95% UCL, so 95% UCL means we are talking about an upper confidence limit which is having a 95% confidence level. Okay, so if, that means if we are talking about 100 samples, 95% samples will always have a value either equal to or lesser, not more. Okay, and there are 5%, 5 samples which can be which can increase that limit. Okay, and that is the significance level. Okay, so how much, that is the alpha, if you remember, that is the alpha value. So statistical significance level is how much may go wrong. Okay, what is the percentage that may go wrong, and when you subtract that with 100, you get the confidence level. Okay, so that is the 95%. So alpha here is 5%, and confidence level is 100 minus 5, that is 95%. Okay, sorry. So if we talk, so basically this is the equation for calculating UCL. So UCL 1 minus alpha is equal to mean plus T alpha n minus 1 into standard deviation by square root of number of samples. Okay, so if you see here, this alpha is not, in this case the alpha is not confidence limit. If you remember, when we calculated method detection limit, when we talked about method detection limit, that was the value was equal to t into s, right? T was the same student t statistic, and s was the standard deviation, but there alpha was basically the confidence level. However, in this case, it is the significance level. Okay, the statistic significance, this value, statistical significance level. So that alpha is basically, it is a probability that the results would not be the same or wrong if repeated multiple times. So wrong means basically it will be higher. Okay, so if we are talking about 95 in this case, basically upper confidence limit. So if you are talking with 95% surety that this is the upper confidence, upper limit, so there will be, out of 100 samples, there will be maximum of 5 samples, there can be maximum of 5 samples which can have a value higher than that. Okay, so that's why that will mean that it is having a alpha value of 5%, and generally we always take a confidence level of 95%. That means we allow the chance of 5% to go wrong. Okay, so even for the calculation of so compressive strength in concrete, we always take the characteristic compressive strength, which is basically the compressive strength of 95% guarantee. Okay, so that means out of 100 cubes, 95 cubes will always have that strength, at least minimum of that strength, but there will be 5 cubes which can have a lesser strength. Okay, maximum of 5, not more than. So UCL 1 minus alpha is basically, this 1 minus alpha is the confidence level. So UCL 95%, 1 minus alpha equal to mean plus T alpha n minus 1 into standard deviation by square root number of samples, where T is the student T statistic. So for example, if we talk about the UCL value for 95% confidence level, so as I told you, so for this to be 95%, the alpha has to be 5%. Okay, so alpha is 5%, that is 0.05, and so UCL 1 minus 0.05 equal to 4.83. So that was basically the mean value for the data set 1. Okay, if you remember, and plus the T alpha n minus 1, so that is the student T statistic at 5% of alpha, and 28, that is n minus 1, 29 minus 1, 28 degrees of freedom of n minus 1 value, and that is basically for one tail test. Okay, so generally there are two types of tests. One is in T statistic, there are two types of tests. One is one tail test and one is two tail test. Okay, so for one tail test, we will get the value for T is 0.05 and 28 to be 1.701, and we are considering one tail test because we are talking about the upper confidence limit only. Okay, if we would have talked about both the upper as well as lower, okay, so that value would have been then it would have been two tail test. Okay, then it would have been now this 5%, it is completely on the upper side. Okay, But when we talk about two tail test, then it will be, if we talk then also, if we say 5%, that means 2.5% will go to up and 2.45% will be down. Okay, but here, because we are talking about one tail test, the 5% is completely above the upper confidence, okay, upper limit. Okay, so therefore, based on one tail test, taking 0.05 and 21 28, the t value at 0.05 and 28 is 1.701, and into the standard deviation, yes, so standard deviation was 2, if you remember, for the first data set, and square root of 29, which was the number of samples. Okay, so that comes to be out, so there it comes, so taking this, it comes to be a value, the value of UCL 95% comes to be equal to 5.46. Now if you remember, the TC limit was given as 5. Okay, and we have got a value of greater than 5. Okay, so that means, taking into uncertainty, there is chance that our value will get higher than the toxicity limit. Okay, toxicity characteristic limit. So similarly, if we talk about the second data set, if we again find out the value UCL at 95% confidence, so here in this case, what will how to find it? So we have to use the transform data. Okay, and then we have to again come back. Okay, as we just discussed few slides back, how to find the value when it is transformed back. So when it is transformed back, the value which is obtained, that is equal to the geometric mean. Okay, but we will like, if we even consider the this one, in this case we can directly consider the e to the power 1.65 value, and that will be equal to 5.19. Okay, and the UCL value for the transform data set, that will be equal to 1.46, which was the mean of the transform log normal transform set, plus 1.697. So that was basically the t alpha n minus 1 value for 0.05 and 30, that is n minus 1. So t 0.05 30 for one tail test, it will be 1.697, and into 0.65, which was the standard deviation, by square root of 31, which was the number of samples, this is 1.65, and by transforming back basically, so if log e UCL value was 1.65, log e UCL 95 was 1.65, then UCL 95 for the actual data set, it will be e to the power 1.65. Okay, so that is equal to 5.19. Okay, so here we cannot find a geometric mean, because geometric mean is only related to arithmetic mean. Okay, when it was transformed back, so taking e to the power arithmetic mean was equal to taking e to the power arithmetic mean of the transform set was equal to the geometric mean of the actual set. Okay, so that was a relation, but in this case we can't use the geometric mean, we have to directly find it out from the 1.65. so log e UCL 95 is 1.65, 95%, so UCL 95% will be directly e to the power 1.65, which is 5.19. Okay, so this is the UCL value for the actual data set. So now let us see the data below the detection limit. Okay, so what to do about the data below the detection limit? So in many cases, sample results will be below the analytical instruments detection limit. Okay, so as we just found, like in the start, if you remember, we calculated the MDL value, so that was the detection limit. Okay, method of detection limit. So you will see that in many cases the sample results will be below the analytical instruments detection limit. So if you have the BDLs, that is the below detection limits, in your sample set, you must handle them appropriately with statistics. Okay, so it is very important to handle them appropriately with statistics. Otherwise, we will have a wrong idea of the distribution. Okay, so you cannot just neglect them. They say something very valuable about the data, so we just cannot ignore them. They always say something very valuable about the data. Okay, so therefore, it is very important to handle those samples, or the values of those samples which are below the detection limit. Okay, so what to do, what are the options of handling those samples or the data sets? Okay, the data or those samples which are below the detection limit. So basically there are four ways, okay, to handle them. One is, let us assume it to be 0. Okay, so if it is 5.17 milligram per liter and we are getting it, say let's say about 1 or 2, so let us assume it to be 0. Okay, that can be one way. Second is to assume to be the detection limit itself. Okay, so if we are getting it to be 2, okay, let us, if it was 5.17, let us take it to be 5.17 itself, or it can be assuming to be half the detection limit. So if it was 5.17, let us take it half of 5.17. Okay, And one more way can be more rigorous statistical approaches. Okay, so many other statistical, very advanced statistical approaches are there, which are very rigorous, and but those are beyond the scope of this course. So those are also available. You can always you are welcome to study that also. Okay, so now let us go into the sustainability and LCA basically. So these were the concepts, statistical concepts related to data collection and uh, how to handle data. And these are sufficient for our environmental science related prospects. Okay, so aspects. So this much is the idea that is required. Now let us go into LCA methodology. So before that, what does it mean to be green? What is sustainability? Let us look that. So sustainability, basically, as per the UN World Commission on Environment and Development in 1987, that was the Brundtland Commission. So they defined the sustainable definition as development that meets the needs of the present without compromising the ability of future generations to meet their own needs. Okay, so that is a very famous. It's a very famous definition. Sustainability means development that meets the needs of the present without compromising the ability of future generations to meet their own needs. And basically it means being environmentally friendly, using sustainable products, using green products, and always being environmentally preferable. Okay, so using things which are environmentally preferable, or products which are environmentally preferable. And how some of the ways to achieve that is using biodegradable materials, uh, using recyclable materials, using ozone friendly materials, using eco design or ecology uh, friendly design related materials, and also going for greenwashing. It is spending on advertising an organization or a product which is green. Okay, so that can also be done. So that will also make other people aware also. So why is this important? Okay, so why it is important? That is because of the that is basically related to why, like, apart from the sustainability part, one of the most important part related to the art is the population. Okay, so population is a very big problem in the current scenario. So why it is a big problem? Let us check this. So what can the art handle? So as per some estimates, Art's maximum supportable population is about 13.4 billion. Okay, and I think we have already crossed 8.5 billion, right? So, so this is the maximum. So we are almost near to that. Maximum supportable population is 13.4 billion. We have reached about 8.5 billion. So we are close to that. So looking at the population statistics, where are we headed? So that is a very big problem. So one of the main factors of why these issues of sustainability and environmental life cycle methodology or environmental science is coming is one of the main reasons for coming for these things to arise is to these topics to arise is the population basically. Okay, so population is a very the explosion of population is a very big issue. So looking at the population statistics, where are we headed? So yeah, one of the issue of using renewable energy sources, it will limit our growth, because that is because it is very costly, and also it is not that much efficient as compared to the non-renewable energy sources as per now. Okay, things may improve, it definitely will improve in the future. So world population statistics, UN population division, as per the world population statistics of the UN population division. So as per 2007 data, so it was found that in the whole world the annual growth was 6.7 billion. Okay, and out of that 5.4 billion came from the LDC, or the less developed country, with a rate of the growth rate of 1.44%, which was higher than the world growth rate. Okay, which was 1.24% between the 2000 and 2007 duration. Okay, however, only 1.2 billion was it 1.2 billion out of 6.7 billion growth was coming from the more developed countries, with a very much less annual growth. Okay? 0.36% as compared to 1.24%, it is nothing. And US also contributed to 301 million growth, okay, in that time, okay, in 2007. And it also, between 2000 to 2007, it had a growth rate of 1.03%, which was a little high, but still very less than 1.24%. Okay, but if you check about low developed countries, it is very higher than 1.24. It is about zero point 0.2 times zero point 0.2 more. Okay, 0.20% more. So that was higher. So that is the problem of this one, the problem of low developed the uh, underdeveloped countries. So more is the underdevelopment, more is the population. Okay, so that is it is very much interrelated. Okay, so because they have very less awareness of all these concepts. And if we talk about the average per capita energy consumption, globally it was 3 kilowatt per person per unit time. And but however, in US alone, the consumption was 4 times that. Okay, so 4 times the average. It was 12 kilowatt per person. In industrialized places, it was 2.5 times, which was 7.5 kilowatt per person. In Denmark, it was more than 1.5%, which was 5.1 kilowatt per person. However, in developing, it was about 33%. Okay, 33% of the average value, that was 1 kilowatt per person. So less developed countries used less capita energy consumption, had a less capita energy average per capita capita energy consumption per capita. However, the more developed countries had a higher energy consumption per capita, which was led by US, which was 4 times more than the average value. Okay, so being green is trendy. However, what does science say? Okay, so industry is looking for ways to green their products and manufacturing processes. Individuals and families are looking to green their homes and lifestyles. However, how can you tell if something really is green, and what is currently happening to achieve this goal? Okay, so we are always looking for finding avenues which are green, products which are green, processes, manufacturing processes which are green. Okay, individual families are looking for green lifestyles and green homes, but how can we really say that it is green? Okay, what is currently happening to achieve this goal? And the answer to this is scientists perform a LCA, which is life cycle assessment. Okay, so the answer to find answer to finding out whether any product or any process is green is by performing a life cycle assessment, LCA. So what is LCA? That is a scientific way to look at going green. Okay, so you can, if we briefly say, it is a scientific way. Loosely, if we say casually, it is a scientific way to look at going green. That is LCA. And if we check out a technical definition, LCA is basically compilation and evaluation of the inputs, outputs, and the potential environmental impacts of a product system through its life cycle. Okay, so it is basically compiling and evaluating the inputs, outputs, and the potential environmental impacts of a product system throughout its life cycle. That is life cycle assessment, and this establishes an environmental profile of the system. And as per the ISO, which is the International Standardization Organization, so it ensures that an LCA is completed in a very certain specific way. And how it is useful, what can be done with LCA? So product, it can lead to product or project development and improvement. It can help in strategic planning. It can also improve public policy making. It can make marketing and eco declarations more effective and efficient. So these are some of the benefits of life cycle assessment. So now let us see what are the methodologies. Okay, so if you see the if you see the basic process. Okay, so this is the product life cycle of any product or material, of any product. Okay, product or material. So product or output, if you check the whole life cycle, it can be divided into this product life cycle, these parts in the product life cycle. One is raw material acquisition, then comes the material processing, then comes manufacture and assembly, then comes use and service, then comes retirement and recovery, and lastly comes the treatment disposal. Okay, so these are some of the chains. Okay, which are some of the chains present in the some of the blocks. Okay, some of the main blocks, main main it these are some of the main aspects. Okay, which is associated with the product life cycle of any product or any uh, any output basically. So in every process. Okay, in every process, every step basically, so we will find that there is some material and energy inputs to the process and distribution. Okay, that is designated by M and E. And basically the W basically, also in every step there is a waste. Okay, which is designated by W. and that waste can be either in gas form, liquid form, or solid form, and that is an output from the product process or distribution. Okay. So every step in the product life cycle has a material and energy input and a waste output. Okay. So the arrow sign basically it represents the material flow of product component. So from raw material acquisition we go to material processing. From there we go to manufacture and assembly. From there use and service. From there retirement and recovery, and lastly treatment disposal. Okay. If here from the steps, okay, and from the relations, if you from the from the arrows coming out of the retirement and recovery, if you check, okay, so if the from directly from the step of retirement and recovery we are going again for a certain product, if we are going again to use and service directly, okay, without going to treatment disposal, so that means we are reusing. Okay. So directly going from retirement and recovery step to use and service, we are reusing. If we are going from retirement and recovery directly to manufacture and assembly, we are remanufacturing. And if we are going from retirement and recovery to the step of material processing, we are basically it basically means closed loop recycling. Okay. So these are some of the aspects which can be done in the product life cycle. And similarly, if the retirement and recovery from that, if we are going directly, we are not going to treatment and disposal, and apart from that, we are going to some other steps. So that means we are going for open loop recycling. Okay. So these are some of the methods which can be used for improving the life cycle of a product. Okay. So now let us see what are the main constituents of a life cycle assessment. Okay, what makes up LCA? So there basically are three parts. Okay, so if we like before that, if we see what is the goal and scope of goal and scope definition, so we have to understand what is the purpose of the LCA and who is the audience. Okay, so that is the main goal and scope definition. And if we go in deep into the LCA, there are basically three parts. One is the inventory analysis, LCI. One is that is life cycle inventory. One is impact assessment, LCIA, that is life cycle impact assessment. And the last is interpretation. Okay. So what does LCI or inventory analysis mean? It means we here we have to find out what is the function and functional unit. Where are the boundaries we have to what are the boundaries we have to keep in mind. We have to check what data we need, what assumptions we are making, and what are the limitations in the assessment. Okay, so these are some of the inventory analysis. The second comes the impact assessment. So here what are the environmental, social, and economic effects from the product, from the development of the product. What are the environmental, social, and economic effects from the product we are uh, uh, basically studying. Okay, so that is the impact assessment. So this is the main part. Okay, like the middle part, LCIA, and the last is the interpretation. That is the interpretation of the results. Okay, and ways to reduce environmental impacts. Okay, based on the result, what conclusions can you draw from the study results? Okay? And what recommendations can be made from those results? Okay, so that is the interpretation. That is basically the conclusion and the understanding. Okay, the discussion. Okay. So one is the input, that is the inventory analysis. What is the function, functional unit, boundaries, data, assumptions, and limitations. One is impact assessment, that is the consequences or the finding the values related to effects related to environmental, social, and economic. And last is like analyzing the results. Okay, interpretation. So how to based on the data result, how to reduce environmental impact, what conclusions can be drawn from the study, and what recommendations can be made. So let us take an example. Okay, let us take an example of the goal and scope. Okay, so let us compare the wooden pencil versus the mechanical pencil. Okay? Wooden pencil which we generally use in our childhood, that is the wooden pencil, and mechanical pencil is the one which is having a, a consistent width. Okay, so it is pressed from above. It has a chain. Okay, spring basically, spring. So the more we press, the depth is the width of the depth of the needle gets increased, and that is used to adjust the our focus, our hand, and the actual it is used to align the pencil and the finger so that we can write efficiently. So let us compare the wooden pencil and mechanical pencil in terms of LCA. Okay, So goal is to compare two writing utensils, okay, for classroom use. So that is a goal, and this is an example between wooden pencil and mechanical pencil. So the firstly we have to see the scope of uh, our goal is to compare two writing utensils for classroom use, and so for that we have to go for each of them individually. So firstly, let us take the example of wooden pencil. So here basically T is representing transportation, okay. So this is the process flow diagram which we just depicted here, product life cycle. So this is the process flow diagram. So in case of wooden pencil, firstly first step is the lumber forest, because it is that place from where we will find the wood, okay, wood or timber for the pencil. Then we will go to lumber mill, okay, so process that wood. Then we will go for manufacturing, so that will use basically rubber, graphite, packaging and brass, okay. So rubber is basically for erasing, graphite is the pencil which we, the that portion which by which we will be able to write, and the black color area. Packaging is basically for selling, and brass is the that metallic metallic that metallic portion which basically holds the rubber to the pencil. So that is the area above the pencil. So these are the substances which will be added in the manufacturing, and then it will be sold to the consumer that is called retailing or retailer, and then we will be using it, okay. So during use we will be sharpening, okay. When the pencil get blunt, we have to sharpen. So for that we need a sharpener, and that sharpener you will have an like that sharpener. For making that sharpener, it will require electricity, okay. So that means electricity is also coming, and finally there will be end of life. So when it we have the the pencil gets finished, okay, it becomes small, so we'll be basically dumping it into the garbage, and that ultimately will be dumped into the landfill, okay. So this is the life cycle of a sorry, this is the life cycle of the wooden pencil, okay. Similarly, if we talk about the life cycle of the mechanical pencil, so here basically the mechanical pencil consists of the writing tip basically consists of polyethylene and polypropylene. Polyethylene is abbreviated as PE, polypropylene is abbreviated as PP. So both these materials are plastic polymers, which are large molecules, and they are used to make many products. So for for making the mechanical pencil, first we will need oil, okay. Then that oil, from the oil, the second step is a procurement of PE and PP. Then comes the manufacture, okay. So manufacturer basically will be using rubber, graphite, packaging and spring, okay. So these are some of the substances which are used for preparing that, and from that manufacturing we will be selling to the consumer, which is retail, and from that they'll be using, and finally there comes the end of life, which is landfill dumping, okay. So we'll not use sharpener here because that is not required. We'll just press from the above, and the tip will get bigger, okay, so that we can efficiently write. So for this, okay, so basically in a inventory analysis, one of the main requirements is the function and the functional unit, okay. So what is function? Function basically is the service provided by a system, or what it does. Roughly we can, if we say what it does, that is the function. And functional unit basically gives the function a number value, and it allows comparison between products, okay. And it is a reference point, okay. So function is the service provided by system, or roughly what it does. And functional unit is a value, okay, which can be used for comparing, which acts as a reference point, and it can be used for comparing some uh, comparing various type of it can be used for comparing the amount of emission, as well as the CO2 release, and every anything related to the environmental aspect between the products, and it can act as a reference point. So it is basically a parameter, okay, by which we can compare products based on various aspects, okay. So if we take the wooden pencil and mechanical pencil example, so the function for both is the writing, okay. So both the the requirement for both was, the need for to have both was writing, and the functional unit we can take one parameter as one number value as 1 meter of writing. Okay, so based on 1 meter of writing we can compare it can act as a reference and we can compare both in terms of what is the longevity. Okay, what is the duration, what is the distance at which it will stop. Okay, writing. So these are some of the aspects by which we can calculate its performance. Okay, so that is the that is the use of functional unit. Okay, it is basically a value which helps us to compare and acts as a reference point. So apart from that, what is the items to consider? Okay, what are the items to consider both in input and output? So input, what is needed to make the substance? Okay, what is the manufacturing requirement, material requirement, as well as the energy, materials, labor, etc. So input is what is needed to make the substance, energy, materials, labor, etc. So material, labor, and energy basically constitutes the input, and output is basically what comes out of the system. So it will firstly, what is coming out of the system is the product. It can be in terms of electricity, materials, goods, services, etc. The second most important thing is the waste. Okay, waste, some definitely some waste will be generated. So what is the waste coming? Thirdly is emissions. Okay, apart from, because we are using various materials, some emission, say CO2 emission or some emission will be directly going to the atmosphere. And fourthly, what are the co-products developed? Okay, what are the byproducts of the actual product developed? Okay, so these are some of the use. Okay, some of the aspects we have to consider basically. Okay? So the data collection, that is the data collection part of the inventory analysis. So it has various this one various parameters through which we have to judge, and we have to find data, collect data. So one is time sensitivity. Okay, so we have to collect data basis, like the data collection collected should be based on at least past 5 years. Okay, so we cannot say something based on 1 day or 1 month or 1 year. Okay, so it has to be a long time duration, so it should be time sensitive. It should be the second important parameter is a geographical parameter. So does it match the location from the goal? Okay, so the say for example we are talking something related to a event which is happening near the seashore. Okay, near the coastline, but we are taking a location which is far away. Okay, in some desert area or in some like central India or some area which is far away from the coastline. Okay, so that will not help us in getting the actual finding the actual life cycle or finding some actual meaningful data, meaningful output. Okay, so geographical factor is important. Thirdly, technology. So what are the best available technology for that process? Okay, so that is important so that we can get a very realistic idea of what is the actual amount of data, what is the actual amount of anything which is coming out. Okay, and so fourth is the representativeness. Okay, that is reflection of the population of interest. Okay, so that is the basically what is the what we studied just back. So okay, so target like representative sample. Okay, so what is a representative sample? So representativeness should be, it is very important. Okay, so that we can designate that value for the entire population. Fifth is the consistency. So that is very much related to the representativeness. So more is the more is the consistency of the match. Okay, it should match the procedure. More is the consistency in the values, better will be the representation. And six is reproducibility. So that is another person should find it. Okay, so if we are doing something and finding, so that should also be found by other person. Okay, so that means it is a very good quality data collection. And in this aspect we should not forget two things. One is precision and one is completeness. So precision is basically the consistent reproducibility of a measurement. So anyone who is doing that measurement, or everyone should get the consistent value, same value. And completeness is covering all the areas outlined in the scope. That is a comprehensive study. Okay, the comprehensive study of the of the goal and what is outlined in the scope. So we are covering every aspect. So say for example, if we are talking about if you are comparing between paper plate and china plate. Okay, so paper plate is the use and throw plate. Okay, and the china plate is the plate which we have in our homes, which we wash and reuse. Okay, So if we compare both in terms of LCA, so we have to answer, firstly we have to answer these types of questions. Firstly, what is the function, okay, function of this, what is the functional unit for this, what can be the materials and resources used for this, what does it take to produce both, okay, what are the impacts to the environment from this, is there waste generated from them, does washing the china produce waste, okay, because the paper plate we are anyways throwing, what types of data do we need for this, how do you know which is better, okay? So based on calculations and the findings, we have to even we have to the we have to our commentary is very important, okay, so what is our commentary, what are our finding, what are our discussion, what is the uh, what we have what output we have generated, how we have based on the obtained result, how we what we have studied, like how we have studied the data, and what new findings we have found, okay, so that is very much important. So say for example, there are various types of categories. So in data analysis, one is environmental impact category. So in this category, there are various types. One is global warming potential. So that is gases in the atmosphere that absorb and emit radiation. They trap heat from the sun, water vapor, CO2, methane, ozone, nitrogen dioxide. So these are some of the examples. So one more category from the environmental impact category is the abiotic depletion. That is the consumption of non-living resources. Sorry. And one is a human toxicity potential, so the value that shows harms to humans from chemicals. And one is land use, how much land is needed, okay. So these are some of the data and like that can be analyzed in terms of environmental impact categories. Sorry. And apart from that, some more data that can be analyzed from environmental impact category can be eutrophication. So that is the increase in chemical nutrients containing nitrogen and or phosphorus uh, in water, basically in water. So it can be both in land or water, but mostly in water, and that results in overgrowth of plants. Okay, it results in killing of organisms at bottom of water because of higher concentration of nitrogen phosphorus than desired. And apart from that, the one more category can be water use, mercury, acidification. So that can be caused by pollution from fuels and acid rain, and also low pH. Okay, and one more urban problem is the smog, okay, that is fog plus smoke, okay. So when fog combines with smoke, it becomes smog, okay. So that is a persistent like that is a perennial problem, be it winter or summer. It is found every time. And one more aspect can be energy use, other can be solid waste as well as oil, and many more are there, okay. So, where do we go from here is a very big question. Okay, so we have to answer that. So, what is the purpose of all this data? Okay, what is basically what is the purpose of all this data, what we are synthesizing from this data, okay? We have to find something important, something new, okay? Something novel. Scientists can make recommendations of choices. So what is the purpose of all this data? So some of the answers can be: one, scientists can make recommendations of choices, okay, which are less impactful to the environment. Second can be scientists can analyze a particular impact and focus on a solution based on that. And third can be industry and individuals can take a closer look at how they can make a difference to this, okay, to the environment based on the data. Okay. So with this, let us come to the end of the course content for the third week and go for the for some of the solved problems, okay, and understand better. So first question, which of the following falls under physical sample preparation? A, mixing, B, oxidation, C, acidization, or D, titration. Okay. So A, B, C, D, out of this, which falls under physical sample preparation? So if you see here, the sample preparation and analysis. So as we studied in the beginning, so there are three parts, right? One is physical preparation, one is chemical preparation, one is analysis. Okay. So if you see, we are being asked what is the which falls under the physical preparation. Okay. So if you see here, the oxidation, it falls in the chemical preparation. So that is wrong. The acidization, it also falls in chemical preparation. That is also wrong. The titration, it comes under analysis, so that is also wrong. So what comes under physical? So that is mixing. Okay, so mixing, A is the correct option. So as you can see, A, mixing, is the correct option. Second question, which of the following is carried out to ensure that the analytical process is reliable for analyzing the test sample? Okay, so which out of this? A, blank; B, replicates; C, spiking; D, control. A, B, C, D. Out of this, which of the following is carried out to ensure that the analytical process is reliable for analyzing the test sample? Okay, so that comes directly, the answer to this directly comes from the quality control and quality assurance checks. So as you remember, these were designed to make sure that the data gathered are sufficiently accurate, precise, and repeatable. And some of the mechanisms are blank, spikes, replicates, and also control. Okay? So if you see properly, so blank sample will not have the analyte which we are analyzing. Okay, so therefore it will not be reliable. So there is no use of having blank samples. Okay, so A is not the correct option. The D, control samples. So control sample is basically the sample which uh, control sample is basically a sample which value we know. Okay, but analytical process is we are performing analytical process for those samples which we don't know. Okay, so therefore I like the control sample, it may or may not have the actual value which we need to find. Okay, so because these are known values, so we will not be able to completely say whether the analytical process is reliable. Okay, because we already know the value, so we don't have to deduct from something, we deduce from something. Okay, so that is also a wrong option. If you talk about replicates, so replicating is basically simulating a result. Okay, but by simulate, however, by simulating we will not be able to find out whether the analyte concentration which we target, the target analytical concentration, so for finding that whether the analytical process is reliable or not, because it is a replica, it is not the actual one. Okay, so therefore spiking will be the answer. Okay, but as we all know, as we discussed, what was spiking is adding something known concentration. Okay, it is adding something known concentration for a in a sample, and checking whether the values are matching the values obtained in the chart. Okay, so if by increasing the known amount, if we are finding the values to be equal, so we can say that the analytical process is reliable for analyzing the test sample. Okay, so the C, spiking, will be the correct option. So as you can see, C, spiking, is the correct option. Okay. Third question: which one of the following statements is or are correct? A, in HPLC, that is high performance liquid chromatograph, compounds are compounds are separated based on their density. Okay. B, atomic absorption spectrometry works on the polarity based separation principle of compounds. C, cations in water sample can be measured using ICP. And D, ion exchange chromatography is applicable for ionic or polar compounds. Okay, so out of A, B, C, and D, which of the following are the correct statements? Okay, so let us study the hints. So basically, ion exchange chromatograph. So it is used to analyze liquid samples for dissolved ionic or polar materials by charge properties. So it is used for finding ionic or polar materials by charge properties, ionic or polar compounds. So D option is correct. Okay. The inductively coupled plasma ICP. So ICP AES is used to analyze elements such as heavy metals and cations using an inductively coupled plasma ICP. Each element can be recognized by electromagnetic radiation produced by excited atoms at a wavelength of a particular element. So they can be used for metals and cations. Okay. So if you see here, cations in water sample can be measured using ICP. Okay, because they can be used to analyze elements such as heavy metals and cations, and there is nothing related to whether it should be solid, liquid, or gas. That means it can analyze everything. Okay, so that means cations in water sample can be measured using ICP. So C is also correct. So C and D both are correct. And then high performance liquid chromatograph, HPLC. So if you see here, HPLC is used to separate complex chemicals to single components, and it uses liquid as a mobile phase. uh, they are detected by UV VIS absorption detector, and it can handle liquid samples. More complex and greater molecular weight chemicals can be analyzed. So here it is written, in HPLC compounds are separated based on their density. Okay, but if you see here, it is a liquid chromatograph. Okay, high performance liquid chromatograph. So what is the principle of liquid chromatograph? So it will separate the single components based on their diffusion characteristics and flow properties. Okay, in the liquid phase. So that will be the separation will be based on diffusivity and flow parameters, not on basis of density. So A is not the correct option. C, D is correct. A is not correct. Let us check about B. So, as the name suggests, atomic absorption spectrometry works on the light absorption spectroscopic principle. But here it is written, atomic absorption spectrometry works on the polarity based separation principle of compounds. So, polarity based polarity based separation principle of compounds, this works on spectrometry. Okay, so not on polarity based separation principle. So therefore it works on light absorption spectroscopy principle. Therefore B is also wrong. Okay, A and B both are wrong, C and D are correct. So out of the following statements, which are correct? C and D. As you can see, C, cations in water sample can be measured using inductively coupled plasma, and D, ion exchange chromatography is applicable for ionic or polar compounds, are the correct options. Fourth question, which of the following is a measure for central tendency? A, mean; B, median; C, mode; D, all of the above. So out of this, which is a measure of the central tendency? A, B, C, D. So, if you remember, what is the representative concentration? So, some estimate of the central tendency can be both. It can be all the three: mean, average, median, middle number, most common number, and also even some upper or lower confidence limit. And if you remember, we must consider sample distribution and data, where the data will be used for before considering. So, if you talk about the conventional case. Okay, so both all the three can be an estimate of the can be a measure for the central tendency. Therefore in the conventional case, all of the above are correct, and because nothing is mentioned, it is a conventional case. Okay, so it is a normal case. Let us assume normal distribution. So D, all of the above is the correct option. So as you can see, D, all of the above, that is mean, median, mode, all are the correct options. So D, all of the above is correct. Fifth question, which what is the geometric mean of a data set which is actual, showing log normal distribution with an arithmetic mean of 1.32. Okay, so that is the transformed. Okay, log normal distribution, there is a transformed log normal distribution has an arithmetic mean of 1.32. So what is the geometric mean of the actual data set? So is it A 1.32, B 0.66, C 2.64, or D 3.74? A, B, C, or D? Out of this, which is the correct option? So if you remember the geometric mean, when the mean of the transform data is transformed back, this is known as the geometric mean. So the geometric mean is equal to e to the power arithmetic mean of the log transform data set, which is equal to e to the power 1.32, that is 3.74. So D 3.74 is the correct option. Okay, so D 3.74 is the correct option. Sixth question, a team of 4 researchers went to collect soil samples to analyze the arsenic level in the soil of a construction and demolition site. After analyzing the data, they went to report that to the supervisor. Based on their comments, the supervisor suspected that one of them did not participate in the analysis. Can you identify the researcher based on their comments? Okay. So a researcher A, we collected statistically significant number of samples from different locations at the site to account for the heterogeneity. B, researcher B, we analyze all the samples and all are showing detectable presence of arsenic, that is more than 0. C, researcher C, we analyze the samples and got few below the detection limit of the method, so treated them as 0. D, researcher D, we spiked few of the samples to check whether our analytical method is reliable or not. A, B, C, D. So we need to find out which is the researcher that supervisor suspected to not participate in the analysis. Okay, based on the comments, we have to find out the researcher who, according to supervisor, has not done the research, not done the analysis. Okay, so let us see. So basically, if you see here, the researcher A, he or she collected statistically significant number of samples from different locations at the site to account for the heterogeneity. So that is true. Okay, so you have to collect a significant number of samples to account for heterogeneity. So researcher A has participated in the analysis correctly. So let us see D, researcher D. We spiked few of the samples to check whether our analytical method is reliable or not. So that is the correct way for checking the analytical method by spiking. That is adding a known concentration and then seeing whether the increase is correct or not. Okay. So that is the this one. Uh, that is that is correct way to find that out. So researcher D is also correct. So that means he or she has also participated in the investigation. Let us see researcher C. We analyzed the samples and got few below the detection limit of the method, so treated them as zero. So as they got below the detection limit, okay. So as if you remember, so options for handling samples below the detection limit, so it can be assumed to zero. It can be assumed to be the detection limit half the. It can be assumed to be half the detection limit, and also we can use some other statistical approaches. So it can be assumed to be zero. Okay. So he or she has treated them as zero, so that is also correct. So researcher C is also correct. That means he or she has also performed the analysis. So let us go for fourth option, that is researcher B. We second option, researcher B. So we analyze all the samples and all are showing detectable presence of arsenic that is more than zero. Okay, so this is not a correct answer. Okay, so this is not a correct statement because if he or she has found detectable presence of arsenic, okay, so that means it should be more than the detection limit, okay, not zero. Okay, it should be more than detection limit and not zero. Okay, so that is also mentioned in this one, method detection limit. So minimum concentration of substance that can be measured and reported with 99% confidence that the analyte concentration is greater than zero and is determined from analysis of a sample is in a given matrix type containing the analyte. Okay, so if it is detectable presence, it should be more than detection limit, not zero. So B is the researcher who has not done his analysis. Okay, who did not participate in the analysis. So he is the culprit. Okay, so this is the researcher. Okay, so this is the identification of the researcher. It is researcher B. So B is the correct option. So as you can see, B, researcher B, we analyze all the samples and all are showing detectable presence of arsenic that is more than zero is the correct option. Okay. Seventh question, which of the following can be selected as a functional unit when conducting a comparative life cycle assessment of two carbonated drinks, brand A versus brand B? A, 1000 consumer, B, 1000 liters of carbonated drink, C, life of carbonated drink A, or D, life of carbonated drink B. Out of A, B, C and D, which is the correct option? So here we need to find out uh, which of the following can be selected as a functional unit. Okay, for two carbonated drinks. Okay, life cycle, for comparing life cycle assessment of two carbonated drinks. So which can be taken as a functional unit as a parameter for evaluating, comparing, and reference. Okay, points between brand A and brand B. So life of carbonated drink is can be a parameter, functional unit. So C is not the option. Life of carbonated drink B, that cannot also be a parameter. So D is also not an option. It is not a functional unit. So D and the C and D are removed. 1000 liters of carbonated drink, so that can be a parameter because 1000 liters is a parameter which can be compared, which can be taken as a reference point. So B is correct. And A, 1000 consumers, so that can also not be taken as a functional unit because it is not consistent. Say for example, one consumer can drink 5 liters of the carbonated drink. The second consumer can drink, say for example, 2 liters. Third consumer can drink 10 liters. So it is not consistent. So that means we will not be able to compare and take it as a reference point. So A is not the correct option. So A, C and D are incorrect. B is the correct option. B, 1000 liters of carbonated drink. So if you remember, functional unit is, it gives the function a number value, allows comparison between products, and it also acts as a reference point. Okay, so B, as you can see, B, 1000 liters of carbonated drink is the correct option. Eighth question, match column A with column B to choose the correct option. Column A, 1 environmental effect, 2 goal and scope of LCA, 3 recommendations. Column B, 1 system boundary, 2 interpretation, 3 LCIA. So A, A1, B1, A2, B2, A3, B3, B, A1, B2, A2, B1, A3, B3, C, A1, B3, A2, B1, A3, B2, or D, A1, B3, A2, B2, or A3, B1. So out of A, B, C, and D, which is the correct option? Okay. So if you remember this slide, so what makes up LCA? So the goal and scope definition. So there are three parts inside LCA. One is inventory analysis LCI, one is impact assessment LCI, and one is interpretation. Okay. So if you see here, environmental effect. Okay. So environmental effect basically comes under the impact assessment. If you see LCI, it is the environmental effects. Okay. Environmental, social, economic effects. So one is matching three. Okay. A1 will be uh, A1 will be related to B3. Okay. So A1 B3. So out of C and D, one will be the correct option. Okay. So second is goal and scope of LCA. Okay. So goal and scope of LCA. So that will be so that is basically coming in the inventory analysis. Okay. So that will basically include system boundaries. Okay. So if you see goal and scope, okay, so it up inside it, so it comes under inventory analysis. So what are the boundaries involved? Okay, so we have to find the limitations as well as the boundaries which we are using to compare. Okay, so two is related to one, so A2 B1. So out of C and D, A2 B1, it is in C. So C is the correct option. And A3 recommendation, so it is coming with under interpretation. So after we find the after we analyze, evaluate, so we have to synthesize, we have to comment, we have to find out, discuss, and we have to find out something new. So that is we have to based on that we have to recommend, we have to predict, and we can do lots of things. So one of the thing we can do is recommend. Okay, recommendations. So as you can see, interpretation, what recommendations can be made from the inside interpretation, what can be the recommendations? One of the interpretation can be the recommendations that can be made. So recommendations is related to interpretation, that is A3 is related to B2. So C, A1 B3, A2 B1, A3 B2 is the correct, A3 B2 B2 is the correct option. So as you can see, C, A1 environmental effect, B3 LCIA, A2 goal and scope of LCA, B1 system boundary, A3 recommendations, B2 interpretation is the correct option. Then ninth question, which of the following is the correct formula to determine UCL, that is upper confidence limit? So A, UCL 1 minus alpha equal to mean minus T alpha n minus 1 into standard deviation by square root of number of samples. B, UCL 1 minus alpha equal to mean plus T alpha n minus 1 standard deviation by square root number of samples. C, UCL 1 minus alpha equal to mean minus T alpha n minus 1 into number of samples by square root of standard deviation. Or D, UCL 1 minus alpha equal to mean plus T alpha n minus 1 into number of samples by square root of standard deviation. So out of A, B, C, and D, which is the correct option? So if you remember the exact formula, it is UCL 1 minus alpha equal to mean plus T alpha n minus 1, student, where T is the student t statistic, into standard deviation by square root number of samples. Alpha here is the significance level, and 1 minus alpha is the confidence level, and n minus 1 is the one less than the number of samples. Okay, n is the number of samples. So if you compare, this will be equal to this. This is the same as this, mean plus T alpha n minus 1 into standard deviation by square root of number of samples. Yeah. B, UCL 1 minus alpha equal to mean plus T alpha n minus 1 into standard deviation by square root number of samples is the correct option. As you can see, B, UCL 1 minus alpha equal to mean plus T alpha n minus 1 into standard deviation by square root number of samples is the correct option. And let us come to the last question. Which of the following falls under environmental impact categories in LCA? A, acid rain, B, eutrophication, C, photochemical smoke, or D, all of the above? Out of A, B, C, D, which is the correct option? Okay. So if you can see here, under environmental impact categories in LCA, So eutrophication is coming, which is increase in chemical nutrients containing nitrogen or phosphorus, resulting in land, can be both in land or water, resulting in overgrowth of plants and killing organisms at bottom of water. So eutrophication is present. Acid rain is also present. Acidification caused by pollution from fuels and acid rain, low pH, and photochemical smoke, that is basically smoke itself. Photochemical is because it is the reactions occur, the chemical reactions occur due to the presence of light. Okay, so photo is light, so photochemical, so that is smoke, smoke plus fog, and it occurs perennially both winter as well as summer because of the industries associated. Okay, so that is also that also falls under environmental impact categories. So all the three, acid rain, eutrophication, photochemical smoke falls under LCA. So therefore D, all of the above is the correct option. So as you can see, D, all of the above, that is all acid rain, eutrophication, and photochemical smoke falls under the environmental impact categories in LC. Okay. So with this, we come to the end of today's class. So let us meet next class next week, Sunday again. Goodbye.